Okay, our topic for today is viscosity. Now, viscosity reflects the resistance to flow due to internal cohesion. So it's the fluid equivalent of friction. So a liquid's resistance to flow is called its viscosity. Now, viscosity is both good and bad. Viscosity, say, for instance, um, enables pens to work because the ink's a bit viscous, so it doesn't bleed all out over the paper. Instead, it stays inside the pen until you push on the ballpoint. But of course, because of viscosity, it takes energy to move through both the air and the water. Now, one manifestation of viscosity is the phenomenon of a boundary layer. That means that a layer of fluid always sticks to a surface. So this could be, say, I don't know, the wall of a pipe, and this is water flowing through the pipe. So what will happen is, as you get closer to the wall of the pipe, the fluid will be at rest, and then very gradually, as you move further and further away from the wall of the pipe, you'll see that the fluid speed builds up and eventually matches the speed of the flow out here in the middle. So this is called a boundary layer phenomenon. Let's try and get those straight. And basically, so we'll just highlight the text here. There's a layer of fluid right next to the surface that does not move. All right, so for instance, in a river, it ends up actually being a parabolic profile where the speed is pretty small close to the bank, and then it reaches a maximum out here in the middle of the river, and then drops down to zero again as you approach the other bank. So that's the velocity of the water particles, the little bits of water in the stream. So what we have then is we have a velocity change over distance, and that's called a gradient. Something that changes over a distance. So we have a change in velocity over a change in normal distance from the wall, perpendicular distance. And this ratio ends up being key to the definition of fluid viscosity. Now let's reverse that earlier experiment around a little bit. Instead of having a stationary surface and a flowing fluid, let's have a fluid that's at rest, and let's pull a surface along. So put, say, a flat piece of plastic and float it on the surface, and then apply a force to that surface. Now that then is going to cause some of the fluid to move as well. So the boundary layer will, of course, move along at the same speed that the surface is moving. And then gradually, the speed of the fluid will drop off down to zero because the fluid down here in the bulk is at rest. Now, we can define, using this setup, viscosity. It's the ratio of the stress that we apply to the fluid over the velocity gradient. And the stress is related to the force that we're using to pull the plate along. So if we rearrange that to try and make sense of it, velocity gradient is the stress over this viscosity. And if you've got a more viscous material, so a larger viscosity coefficient, that means this velocity gradient is going to be smaller. That means that the velocity is going to drop more gradually, i.e., as you pull this plate, you actually pull a lot of fluid along with you. So in a more viscous material, the velocity profile will drop more slowly to zero because the fluid's sticking together and you pull more of it along. So a larger viscosity is consistent with a very sticky fluid. There's lots of internal cohesion and a velocity that drops very slowly to zero in this experiment. By the same token, in a less viscous material, if the viscosity coefficient is smaller, then our ratio, if the viscosity is smaller, our velocity gradient is very big. And a very big gradient just means one that drops very quickly to zero. So for a small viscosity, there's a very large value of the gradient, and the velocity drops quickly to 0. And this is consistent with the fluid that it's not very sticky. So this is the precise definition of viscosity, but ultimately you can see that it's really just related to how sticky the fluid is. So a large coefficient of viscosity is a very sticky fluid. A small viscosity is a not so sticky fluid. Now let's look at units. We've said that this coefficient of viscosity is a ratio of stress to velocity gradient. I said earlier the stress was related to the force. You don't actually need to know this in any great detail in our course, but stress actually has units of force over area or pressure or pascals. Oh, sorry. So actually I want to do the units here, not the symbols. So force is in newtons, area is in square meters. Then a velocity change will be meters per second, and then we're dividing that by meters. So if we simplify that a little bit, we see the meters cancel out here. And so this is newtons per meter squared 1 over seconds. So that is, equals. And so that's going to equal Newton per meter squared times seconds. This is, of course, a Pascal. So it's a Pascal times a second. That's the units of our viscosity coefficient. Now that's the SI unit, Pascal seconds. And then here are some common materials. Water is about 0.001, although it is temperature dependent. Blood is it ranges depending on the consistency of the blood, but it varies between about 2 and 4 times the viscosity of water. And then air is not very viscous at all. Not 1/8 in Pascal seconds. Now there is another common unit of viscosity, which is a poise, and this is I guess an imperial unit of viscosity, and we actually tend to use centipoise because water is about 1 centipoise. So blood will be between about 2 or 3. So you can see there's basically a factor of 1,000 between centipoise and Pascal seconds. And so 600 centipoise would correspond to about 0.6 Pascal seconds. 80,000, there's about 80 Pascal seconds of viscosity. This is for ketchup. And then the air is about, 0.018 or 1.8 times 10 to the minus 2. So a centipoise is 1/1000th of a Pascal second. And it's just easy to carry that thought around in your mind that the viscosity of water is a centipoise. And that's one of the reasons why the units persist. Okay, so yeah, blood for our course in biological physics, this is probably one of the fluids that we're most concerned with. So its viscosity is about 2 or 4 times that of water, depending on the consistency of the blood. Some applications then. So thus far we've got our definition of viscosity. We know its units. It's in Pascal second units, and it's really just related to the stickiness of the fluid. That's what we've got so far. The formal definition there is the ratio of stress to velocity gradient. Isn't going to be particularly important in this course. We just use it to build up our understanding of both the units and of the definition. So it was defined as a ratio of a stress to a velocity gradient. I'll just write the word equation down. And that's about as far as we need to go. All right, so some applications of viscosity then. First of all, drag forces. We said earlier that because of viscosity, it takes energy to move through a liquid. There's actually 3 effects there, as say a ball bearing tries to move through some maple syrup. First of all, that ball bearing is going to compress the fluid at the front side, and there'll be a high pressure region there as a result of that. So the pressure will build up in front, and that means there's going to be a force opposing the motion of the ball bearing. Now, on the back side, there's going to be a low pressure wake because the ball has moved some of the fluid out of the way, so there'll be a little bit less pressure behind it, and so that also tends to retard the motion of the ball bearing. So those two effects added together are called pressure drag. So there's pressure drag, which is these two effects, but there's a third final effect, and that is the fluid has to flow around the sides of this ball bearing, say pushed out of the way by the ball bearing. It's got to flow around and actually exerts a force on the ball bearing as it does so, and that's called skin friction. So there's several contributions to drag then. There's the high pressure region in front, the low pressure region behind, and then the friction of the fluid flowing past the sides of the object. And all of that, all added together, are the force of fluid resistance, or the drag force. Now, one example that you may have encountered of this already is the force of air resistance. So I talked about a ball bearing going through syrup, but this could be, say, a rock falling through the air. There would still be high pressure in front of the rock, low pressure behind, and there would still be skin friction as the air flowed past the rock on both sides. Now, there was a derivation done for a spherical object moving at fairly low speed, and in that case, if the speed is low and the medium is quite highly viscous, then you actually get a drag force that is linear. That means it depends on speed to the first power. And it also, this is just a geometric factor from the surface area and volume of the sphere. It depends on how viscous the fluid is, and it also depends on the radius of the particle. So this is known as Stokes drag, the formula for the drag force on a sphere moving through a viscous medium. Now, it doesn't work very well if the particle is moving really quickly, or if the medium is not particularly viscous. So, say for a baseball moving through air, it's probably not linear drag. This works really well for, say, a ball bearing flowing through syrup. So here's a simple example. We'll ask you to read it, pause the video, work out your answer, and then compare with my answer, which I'll work out right now. So please pause the video and give this example a try. Okay, so from the 5 micron diameter, you can get the radius, and then it's pretty much just simple substitution to calculate the Stokes drag on this white blood cell. It ends up 707 times 10 to the minus newtons. 10 to the minus 9 is a pico, so about a piconewton. That's a typical drag force at the cellular level. So that's one application of Stokes drag. Here's another, and we will work on that one in class. This is, say, finding the terminal velocity of a steel ball bearing flowing through oil. Here's a final example. This one's of great interest in biology. The procedure of gel electrophoresis is a very important experimental tool in DNA research. And basically what you do is you take your DNA and then you digest it, you break it up into a bunch of strands of various sizes, and then you put some of your sample in these little wells here. And what will happen is these fragments of DNA are charged, and consequently, if you apply an electric field by, say, making the top negative here and the bottom positive, there'll be an electric force that will cause those fragments to move. So here we are in top view here, and so if these fragments are negatively charged, then there'll be an electric force on them like this. Now, of course, that's not the only force. There's also a drag force on them that tends to resist their migration. And because the drag force depends on speed, what happens is these particles very quickly reach a terminal constant speed as they move through the gel. But if we analyze that, so we'll say terminal speed, so balanced forces. So the forces sum to 0. So we've got the electric force making them go, but then we've got the drag force resisting that motion. So the electric force just depends on the charge on the particles, which is the same, and the electric field, which is the same for both of them, or for all fragments rather. But the drag force actually varies depending on the radius and the speed. So if we solve this then for the speed, so you'll bring the QE over to the other side, and then you'll divide by 6 pi eta r. And it's that r that's interesting, because what it tells us is that a larger particle, okay, will have a smaller terminal velocity. And we could just highlight that. Larger particles will move more slowly. And that means that the larger DNA fragments don't travel as far through the gel because they're going more slowly. And this means the fragments get organized in proportion to their molecular size, to the number of Daltons in that fragment. And it's based on this that we're able to, say, compare maybe like crime scene DNA versus a suspect. So you would see this suspect here, when his DNA was digested, it ended up matching that retrieved at the crime scene. And here we had a partial match, and here we had, hardly any match at all. So this person didn't do it, but this person here did. So that's the technique, sometimes called DNA fingerprinting. And it relies on our ability to make a whole bunch of copies of the DNA. That's a different bit of biochemistry, but then analyzing it in this gel. And the gel is based on some fairly straightforward physics involving linear drag forces. Here's our conclusion right here. The speed is inversely proportional to the radius, so the larger particles travel more slowly through the gel. Okay, another application of the drag force is quadratic drag. We said earlier that when things were moving quickly, or when the fluid wasn't particularly viscous, that the drag force was no longer linear. Instead, it varied with the square of the speed, quadratic drag. And it also varies with the cross-sectional area of the object, with the density of the fluid, and then there's something called the drag coefficient that we'll get into a bit more in a later course. But this is the expression for quadratic drag. The drag coefficient just reflects the three-dimensional shape of the object. And so, for instance, is it flat? That tends to have a really big drag coefficient. Or is it, say, maybe got like a cone on the front of it, say like an airplane or a bullet? This tends to have a very small drag coefficient. So this might be a drag coefficient of 1. This might be a drag coefficient of, like 0.3. These two things have the same cross-sectional area, but because of the cone in the front here, you get less drag. All right, so a typical example. Again, pause the video, work this out, and then play the video again to see how you did. Okay, so taking the cross-sectional area of the dolphin, about 400 square centimeters, dividing twice by 100 to convert to square meters, we get 0.04 meters squared. And then substituting the value of the density of water, we'll say it's fresh water, even though dolphins swim in the sea, so that will actually be a bit larger. And we get a drag force of about 60 newtons on our dolphin. So, quadratic drag. The final problem of interest. So we've looked at linear drag, Stokes drag. So this is slow moving in a viscous medium. And we just said quadratic drag happens when it's in a less viscous medium or moving quickly. And the next problem of interest from a biological point of view is the pressure drop in pipe flow. So we said earlier that because of viscosity, fluids tend to stick to the walls of a pipe, and that means it takes an unbalanced force to push them through. And that's sometimes called a pressure head. And in physics, the symbol for that is a pressure difference. There needs to be a net pressure. And that net pressure is going to depend on a number of quantities. First of all, you can see that it makes sense that that pressure head should depend on the length of the pipe, very directly with the length of the pipe. It should vary inversely with the radius of the pipe, because as the radius gets smaller, it should take more pressure to put that through. And it depends on a couple of other things. It depends on how sticky the fluid is as well. And we expect that it would take more pressure, more net pressure, a bigger pressure difference to push a sticky fluid through. So those proportionalities are indeed confirmed in Poisson's law, which says that the pressure difference, which is just going to be the difference between those two. So initial must be bigger than final in order to get the fluid to flow through. There's a geometric factor, 8, and then inversely, not with radius, but with radius to the 4th power. It also depends on the volume rate of flow of the fluid through the pipe, because obviously if you want to push more fluid through, you're going to need a bigger pressure head. Now this ends up looking a lot like Ohm's law, because flow of current I, so this is the flow, is proportional to the push and inversely proportional to the resistance to flow. So with the fluid, the flow was the rate of flow, volume rate of flow, RV, and the push is the pressure head. And this then is the resistance to flow. 8 eta L over pi r to the 4th. So just comparing Poisson's law with Ohm's law, V is IR, we can see that it emerges naturally that this term is like electrical resistance. So this is fluid resistance. It's the resistance to the flow in a pipe of a fluid. Now let's look at a very simple example. And we'll deal with blood. So let's say you want to make some blood flow through an artery. You want to get about 2 milliliters per second of it through this artery. And there's the viscosity of blood. So pause the video, try this example, and then compare with my solution. It should be emphasized this is entirely normal. There's nothing wrong with this artery. It's not obstructed in any way, but this is simply saying that you have to have more pressure on this side than you do on this side. Or another way of putting it is that the blood pressure naturally decreases as you get further away from the heart because of the effects of viscous friction. So we convert everything to SI units, 2 milliliters per second. You divide by 1,000 to make it liters, and then divide by 1,000 to make it cubic meters. So 2 milliliters per second is 2 times 10 to the power minus 6 cubic meters per second. The radius is half the diameter. And when you substitute in, first of all, let's go through the units, just because that's good to do every once in a while. So we got meters and meters cubed. That'll cancel out meter to the 4th. The second will cancel, and so all that remains is pascals, which makes sense because we're finding a pressure head or a pressure difference. So that's good. In terms of blood pressure, it's nice to take that number and then just see how it can express it in millimeters of mercury. So we've got 156 pascals. So we divide by 101. 325, and then we multiply by 760 to make it millimeters of mercury. And so you see that's about 1.2. It's about 1.2 millimeters of mercury, a drop over that 30 centimeter long distance, which, you know, is about, say, mostly the length of your forearm. So you expect a certain amount of pressure drop as the arteries carry blood away from the heart due to viscous friction. Now, what if we have an abnormality? What if that artery's radius is cut in half by a blockage? What will then happen to that pressure difference? So we've got a certain delta P that's just healthy due to blood viscosity. But what if that artery is blocked up? So its radius is now cut in half. These are supposed to be the same size diagram, but the radius is now a lot smaller in this one. So what will be the delta P blocked? We're going to do this using proportional reasoning. So does cutting the radius in half, so if this is R, this is half R, what does that do to the pressure difference? Think about that for a minute. It's multiple choice, and then have a look at my answer. Okay, so here it is. The correct answer is that the pressure difference is greater by a factor of 16. Here's the reason why. Because the pressure difference, 8 eta L RV, all of that's staying the same. What's changing is the radius. Now we know it's 1 over the radius to the 4th power. So if you've cut the radius in half, then in this expression, that factor of a half is going to get raised to the 4th power. So you're going to get the same r to the 4, but you're also going to get, in the denominator, 1/2 to the 4th power. Maybe I'll do it like this just for clarity. Now, 1/2 to the 4th power is 1/16. And 1 over a 16th is times 16. So what ends up happening is, and I'll just write this, I guess, several times here. I don't know if it helps the clarity or not. What happens is this is now our original healthy pressure drop. But it's been increased by a factor of 16 when we cut the radius in half in our unhealthy artery. And the factor of 16 comes from the fact that this half radius, that half gets raised to the 4th power and becomes 1 over 16th, which is 16 times greater. So this makes sense. We know that increasing or decreasing the radius is going to have an effect on the pressure. This is just perhaps an unexpectedly large effect on the pressure because it's inversely with the 4th power radius. A small change in the radius due to a blockage has a big effect on the pressure drop across the artery. And ultimately, this is why we have high blood pressure. So we will stop it at this point then, and then pick up these topics together in class.